Behind me stands Milsons Point train station. Like all other train stations around the world, it is a vital link for transporting people as they carry out their daily lives. But as we strive for an ever quicker future, the trains that have been transporting us for centuries are no longer able to keep up. The problem? Friction. The solution? Maglev. The vision of Maglev began in the early 20th century with two men, Robert Goddard and Emily Bachelet. Their dream was to develop a train system that was faster, safer, and more reliable. Thus, they turned to electromagnets. Since then, China, Japan, and South Korea have all joined the race to develop the fastest maglev systems. But what exactly is it that allows these trains to move so quickly? In short, the answer lies in electromagnetism. However, there are currently two very different systems of maglev that provide suspension in two very different ways. The first is called electromagnetic suspension and is used in the current German transrapid systems. EMS uses the attractive forces between iron core electromagnets and ferromagnetic rails. Electromagnets that have current flowing through them are first placed on the underside of the carriage, which creates a magnetic field that is attracted to the stationary ferromagnetic reaction rails that are installed on the underside of the guideway. This attraction results in a distance of just 10 millimeters between the stator and support magnet, which allows the carriage to hover 150 millimeters above the top of the guideway. The train is propelled by the support magnets on the carriage, which provide an alternating current that works to create a series of attractive poles and repelling poles, resulting in forward movement. The second system is electrodynamic suspension and is currently used in prototype Japanese SC maglev trains. EDS relies on the principle of superconductivity, whereby superconductive materials are cooled to extremely low temperatures. These superconducting materials are placed on the side of the train carriage and interact with figure 8-shaped coils on the side of the guideway. When the coils experience the changing magnetic field of the superconductor's motion as the train moves, two currents are induced that oppose the change in magnetic field. One below that creates a reactive magnetic field that opposes the superconducting magnet's pole, and one above that creates a pole that attracts it. Thus, the two forces work together to achieve an approximate levitation of 10 centimeters above the guideway. Propulsion is achieved by a linear synchronous motor, consisting of additional coils in the guideway that provide a three-phase alternating current. The magnetic field created by the superconductor then interacts with this magnetic field to propel it forward. Now that we've explored how maglev works, it is time to discuss exactly why it is better. The problem with traditional trains is that energy is lost through friction. Maglev trains, on the other hand, address this problem by eliminating contact with the guideway entirely. Thus, they have longer lifetimes, lower operating costs, and are able to travel significantly faster and quieter than traditional trains. Furthermore, EMS trains have the added advantage of reduced civilian exposure to magnetic fields when compared with EDS. EDS, on the other hand, is potentially safer as they do not crash immediately into the guideway in the event of a power outage. However, they do not come without shortcomings. For EMS systems, expensive processing computers are needed to ensure that the carriages do not move too close to the guideway. For EDS systems, the cooling of superconductive magnets creates a significant energy cost that decreases its economic viability. There is no doubt that as our society continues to grow, train stations like this will become obsolete. Although the cost of building maglev trains and its accompanying infrastructure is expensive, the speed, efficiency and safety they provide will ultimately become vital as we look towards an ever faster, ever cheaper future.